this is an iHeart podcast. Guaranteed human.
With no fees or minimums on checking accounts, it's no wonder the Capital One bank guy is so passionate about banking with Capital One. If he were here, he wouldn't just tell you about no fees or minimums. He'd also tell you about how Capital One cafes are open 7 days a week to assist with your banking needs. Yep, even on weekends. It's pretty much all he talks about, in a good way. What's in your wallet? Terms apply. See CapitalOne.com/bankguy. Capital One N.A., member FDIC.
Brought to you by the Spam brand.
Some foods or TV shows just instantly take you back to your childhood. Spam Classic is one of those foods.
It's so 90s, but also so iconic that the sight of it sizzling just makes your mouth water.
Back then, we had Spam Classic, but today, there are 12 irresistible varieties to choose from.
It's like picking your favorite Boy Meets World episode. Impossible. There's Korean barbecue flavored, jalapeno, and 25% less sodium, just to name a few.
Spam brand. Sizzle pork and
Learn more and get sizzling at spam.com.
Welcome to Stuff You Should Know from HowStuffWorks.com.
Hey, and welcome to the podcast. I'm Chipper Josh Clark. There's Chipper Charles Bryant. Oh, that's your new nickname.
Chipper Charles?
Yep.
Yeesh.
Yeah, and then there's Jerry.
She's not chipper.
She is actually chipper today.
I'm not chipper. I'm grumpy because this stuff.
I know.
Man, oh man, my head is already melted.
You guys should see the vein in Chuck's forehead. It is protruding.
Well, we'll do our best.
Of course. Dude, we're not astrophysicists, but we do have an astrophysicist coming on as a guest at the end of the episode, don't we?
Yes, my friend, you interviewed Dr. Neil deGrasse Tyson, or as I like to call him, NDT.
Sure, that's what I call him too. NDT, he's dynamite.
Yeah, but I was unable to be on the interview for various tooth-related reasons. Mm-hmm. So you took it upon yourself, and I think an interview like that is probably just better for one person anyway. It gets a little clumsy if two people that don't know anything about astrophysics
right.
are trying to glean information.
Oh, here's my question.
Yeah.
Right.
What'd you eat for breakfast, doctor?
But yeah, it was very kind of him to come on, and we want to thank our friends at the Fox Theater, where he's going to be on April 20th here in Atlanta.
That's right.
For hooking that up. So thanks to everybody who made that happen, because it's a great interview, as you guys will hear at the end of this episode.
Yeah, I loved listening to it, and I'm going to go ahead and say my two favorite parts are probably one that won't make it in when you said that you're happy to plug the Fox Theater show, and he was like, don't bother, it's going to be sold out.
Yeah, I like that too.
And then at the end when you thanked him for advancing our understanding of this light years, and he was like, that's not nearly enough.
Yeah.
He was like, a light year is not very far, thanks.
Yeah. So I changed it to parsecs. He's like, you're getting closer.
I know. It was very funny, actually. Yeah. I hope you leave that part in there.
I hope so. And later on, I immediately regretted not saying, well, you advanced our show billions and billions of light years.
He would have appreciated that.
Yeah, he would have. And I didn't do it.
Yeah.
I wasn't sharp enough.
It was a good interview, though. So
thanks.
Feel free to skip right ahead to that.
We'll lay here and go to sleep. So we're talking about the Big Bang Theory, and not the TV show. So settle down, nerds.
I think he was on that show, though, wasn't he?
I'm sure.
Yeah.
Sure.
Yeah, he made an appearance.
I think all you have to do is say, like, you will further science if you appear on this. He's like, I'll do it.
Yeah, I've never seen one episode of that show.
I guess I've maybe seen some here or there. It's I think, literally the most popular show in the world. Or it was like last season or the season before. Like, it's just taken off like a rocket. And hats off to them too, because they like mix actual science and science jokes and all that stuff. It's like smartening up the world.
Well, I'll tell you one quote I got from Mr. Tyson, Dr. Tyson, from the internet, and it was actually heard him say it, so I know it was a real quote. He said that people asked, "Do you believe in the Big Bang Theory?" And only the way that he can. He was like, well, it's not a matter of believing. He said, I only believe in things that are evidence-based. And he said, the question should be that you posit to people, of all the data and evidence out there, what theory is best supported? And he said it's the Big Bang Theory.
Sure, right. And our colleague Jonathan Strickland, who wrote the article that this is based on, and kudos to that cat, because he took some really, really difficult
concepts and explained it really well.
Yeah, he explained it in a way that I came close to understanding.
Right, same here.
At times.
But he makes that same point, too, that not only is the Big Bang Theory a theory, which obviously cannot be proven, can only be disproven, but that there are other competing theories out there, too, which we'll talk about later.
Sure.
But that, for the most part, it has the most observational evidence backing it up, including the recent confirmation of gravitational waves, which made a huge stir. And that, as a result, it's the most widely subscribed to theory among scientists as describing the early universe. And that's a big thing. There's a big distinction about that. A lot of people think that the Big Bang describes the formation of the universe.
Not true.
No. The Big Bang describes the time starting very soon after the universe formed. But it does not go back into where the origin of the universe came from, what came before it.
No.
And it actually doesn't even go all the way back to that point where everything started. It just can't, because science falls apart, as we'll see, the further you try to go back in time, because, time ceases to exist at that point.
Yeah, if the universe were a human being, it's the Big Bang Theory sort of describes the point where the sperm and the egg meet up.
It describes the time a trillionth of a second after they met up. What about that?
Yeah, which is,
It's close.
It's a pretty great time.
It is. So another misconception, Chuck, is that the Big Bang was an explosion. That's not correct.
No, in fact, a man named Sir Fred Hoyle is the one who gave it a name not almost, he gave it to it in jest as sort of an insult, because he was a believer, or I don't know if he always was, but he was a believer at the time in the steady state theory.
Sure.
And it was like, this explosion, this Big Bang.
Yeah.
But it's not an explosion at all.
So, Chuck,
it's a rapid expansion.
It was, and the best way to think of it is like this. So, like an explosion, right? Let's say you have a planet, and that planet is actually the universe, and it's just floating there in space.
Sure.
And Darth Vader shoots it with the Death Star, and it goes, poof, right?
Uh-huh.
And it goes everywhere.
Yeah.
Starts scattering everywhere. But it's scattering within the boundaries, the confines of space as we understand it.
Sure.
That would be the popular conception of what the Big Bang represents. Not at all.
No.
What the Big Bang actually says is that space itself inflated.
Yeah.
It expanded. And that all the stuff that was in it was in this very tightly wound, dense, incredibly hot core that was a singularity, basically, that expanded into the universe that's as big as we understand it now.
Yeah, something that was so tiny and hot, it had an infinite amount of density, because everything we know was crammed in. You know what it's like? It's like, if Neil deGrasse Tyson listens to this, he's going to love this.
Okay.
You know the little pellets that you would get with your fireworks, a little black pellet?
Uh-huh.
And then you light it.
A smoke snake.
And then it snakes out to several feet.
Right.
That's like it, except if that pellet were like thousands and thousands and thousands of fraction of the size of a head of a pin.
Right. I think that's a great analogy.
And I'm just going to leave the room.
Right.
And I'll come back in 40 minutes.
But even still, Chuck, take that analogy, right? When you imagine that snake growing on a sidewalk, and maybe there's kind of grass in your view, and it's at night, and there's a car parked there because you're outside, right?
Well, sure.
That's where our brain wants to take us.
Yeah.
We want to confine what we know within the boundaries of our universe. What we're talking about is the universe itself growing.
Yeah,
and expanding in nothingness.
Yeah, and he points out in the interview, I don't want to spoil it, but he kind of blows my mind when he starts talking about, this goes beyond what our human senses can understand.
Right.
Sight and sound, forget about it.
Yeah. And that's how nobody's going to be able to pin anything on us, because we'll be like, well, we just can't comprehend that, so how could you blame us for getting it wrong?
Yeah.
So, Chuck.
Whew. Now I'm going to leave the room.
Okay.
And you need what, a half an hour?
It may take a little longer than that.
No, I get parts of it, so I'll just chime in when I feel confident.
There's a line, right, that Strickland had in here. It was, he says, at the earliest moments of the Big Bang, all of the matter, energy, and space we could observe was compressed to an area of zero volume and infinite density. Doesn't that sound like the line from a religious text or something like that?
Yeah.
Isn't it just like right there on that border between like science and religion, basically?
Yeah, like, and now take this drug and everyone take their clothes off and follow me
Right, exactly.
into the grand room.
And we'll understand what I'm talking about.
Yeah, and you know what? When Strickland and scientists and cosmologists talk about that is what is known as a singularity.
Right.
That thing with zero volume and infinite density.
Right. So, I think it bears repeating at least one more time. What we're talking about is all of the matter, all of the energy, all of the heat, all of the radiation, everything in the universe that is here or ever was here over the last 13 point roughly 7 to 9 billion years.
Yeah.
Was in a point that was 23 orders of magnitude smaller than the diameter of an atom.
You just caught yourself wanting to say it's like a little ball, but there's not even circularism.
Right, yeah.
Is that a word?
Yes.
There was nothing circular.
And so at this time, at this point, we know that it was very, very hot.
Sure, makes sense.
Like mind-bogglingly hot. Like you can't even think of all the zeros associated with the degrees of Kelvin or Fahrenheit or Celsius, right?
Right.
And it was incredibly dense. And then something happened. We don't know what that was. Science simply isn't equipped to explain it or understand it or detect it.
Right.
Something happened to make this incredibly dense ball, or whatever it was.
Yeah, there was no ball.
Expand.
Yes, and it was not like the smoke snake. It wasn't a child with a lighter.
You don't know that? Neil deGrasse Tyson doesn't know that? Nobody knows that.
So this expanding happened really, really, really fast, and we'll talk later about just those first few seconds afterward. Like, that's how fast we're talking.
Well, few, like, trillionths of a second is how they break it down. Like, so much happened in that literally the first second of the origin of the universe.
Yeah.
That there are different ages and epochs that happened in, like, trillionths of a second.
It's really mind-blowing. So, as things expanded, though, in those first few seconds, and today, things are still expanding.
Right.
Things are expanding and things are cooling down, even as we speak.
Right.
Literally every second that we're on the Earth, we're expanding, and, well, not us, but the universe is expanding and cooling.
Right, exactly. And as a matter of fact, from what I understand, our region of the universe, which is something like 90 billion light years across, is no longer expanding, but other parts of the universe are expanding.
Right.
And there's this really great article about cosmology and where it stands right now. It's in Aeon.
Not cosmetology.
No, cosmology.
Yes.
And it was written by a guy named Ross Anderson, and I think it's called In the Beginning. And it's incredibly well written, but he makes a really great analogy. He says that 90 billion light year across portion of the universe that we inhabit, that we consider our own, is but a small section of one tiny bubble that floats along on a frothy sea whose proportions defy comprehension. Isn't that neat?
Yeah.
And that's just our section of the universe, right?
That's our little neighborhood.
So the universe is unknowably large. We sound like H.P. Lovecraft here describing this stuff.
Yeah.
And still, some parts of it are expanding. And apparently in the early universe, when it was a singularity, the four fundamental forces.
The dark side? Right. Oh, wait.
Yeah.
I thought you meant the Star Wars universe.
Yeah, I was.
Oh, okay.
Yeah.
So the Force, the dark side, midi-chlorians.
And Mark Hamill's hair.
Yeah, and prequels. The four basic forces, as everyone knows, electromagnetism, strong nuclear force, weak nuclear force, and gravity.
Right, and that singularity before the universe began to expand, all of them were coupled together into a single unified force.
Yeah, which we don't understand how.
No, we don't. And as a matter of fact, trying to get them back together is one of the great pursuits of physics. Mm-hmm. Because if we can figure out how they were all unified, we can start to understand the science we need, the paradigm we need to understand the origins of the universe, but we just can't figure out how to do it, right?
Yeah, one thing that kind of blows my mind with this is when, we get to the stuff later on about does it defy other laws of physics and stuff? Like, basically, every answer is like, the further you travel back toward that singularity, the less all these rules that we think we understand apply.
Right, it falls apart.
Yeah, so just, we'll probably never understand this stuff.
Yeah.
At that very singular moment.
Yeah, I don't know. I disagree. I think I disagree, yeah. I think that we are maybe a century or two away from understanding it.
Well, you just clearly pulled that out of your hat.
Well, I totally did.
Oh, okay.
But we've made
another 126 years.
Well, no, we've made some incredibly huge strides in the last, 150, 200 years in our understanding thus far, right?
Yeah.
So I think that's not a bad guess, right?
So it'd be a string theorist, right? To marry all these,
I don't know.
Probably.
I don't know, and that's what NDT said. That's what we call him now.
Yeah.
That's what he said. He was like, who knows? It could be string theory. Maybe someone will be able to come up with a unified theory, or what's called a theory of everything, that unifies the four fundamental forces back into their single version of a force.
Man.
Or maybe we just don't understand quantum physics enough quite yet.
Yeah.
And when we figure that out a little more, that will unlock some keys for us.
Unbelievable.
So, Chuck, before we get into how we started to come to understand the Big Bang and the origin of the universe, let's take a break real quick, all right?
I'm going to go wipe my brow.
You're doing great.
Brought to you by the Spam brand.
Some foods or TV shows just instantly take you back to your childhood. Spam Classic is one of those foods.
It's so 90s, but also so iconic that the sight of it sizzling just makes your mouth water.
Back then, we had Spam Classic, but today, there are 12 irresistible varieties to choose from.
It's like picking your favorite Boy Meets World episode. Impossible. There's Korean barbecue flavored, jalapeno, and 25% less sodium, just to name a few.
Spam brand. Sizzle pork and
Learn more and get sizzling at spam.com.
#1 hits, millions of records sold, awards, sold-out tours. You think the Jonas Brothers are satisfied? Nope. It's podcast time.
We get to ask other people questions because we're sick and tired of being asked questions.
Hey Jonas is available now, and their first guest is a big one, Paul Rudd.
You know, Steve Carell is a great singer.
Didn't he tell you not to audition for The Office or something?
I told him.
Whoa.
We were filming Anchorman. Clearly, I was the idiot. Thank God he didn't listen to me, right?
Listen to Hey Jonas on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts.
Learning stuff with Joshua and Charles. Stuff you should know.
All right, I sort of get this part, so
the history part.
I'm going to talk a little bit about it. And this makes a lot of sense to me. You go back in time. Let's get in the Wayback Machine.
Oh yes, let's.
Boy, it feels so safe and comfortable in here.
I know. Stinks of kerosene.
It does, weirdly. It's the 1800s, and astronomers started using something called a spectroscope, which is pretty nifty. We've talked about light waves in here before. A spectroscope is something that divides that light spectrum up into the wavelengths, blue on the left, red on the right, and as you go further toward the red, the wavelengths grow longer. So that's part one.
Right. That was spectroscopes.
Yes, that's light waves.
Right, and around the same time, a guy named Christian Doppler was tinkering with the frequency of sound waves, right? He was studying those.
Because he's a smart guy.
He is.
And he said, you know what? It's weird that when I sit by a train, it sounds different as it goes by me, approaches, then goes by me and goes further away from me.
Right, it sounds different, then that doesn't really make any sense.
Yeah, and whereas most people would just eat their figgy pudding and go about their day, right. He wanted to try and explain it.
He was like, anybody else would have been like, this new Charles Dickens book is top notch.
So he said, you know what, as this noise approaches you, the sound waves it generates compress, and it's going to change that frequency, or at least how you perceive it, in a different pitch. So as it moves away from you, those waves are going to stretch, that pitch goes down, and I'm going to name this effect after myself.
Right. Well, I'll let my wife do it, so I don't look like a jerk.
Right. So basically you marry these two things, light wavelengths and the Doppler effect.
Right.
And it sort of led us down this path to where we could understand the Big Bang Theory.
Right. It would indicate that something that was emitting light out there in the universe, whose light moved toward the red end of the spectrum, would be emitting longer wavelengths, which would suggest, based on Christian Doppler's findings, that it was moving away, right?
Yeah, and they found that. They said, look at these stars. Some of the light is falling into this right-hand side, and does that mean it's moving away and it's getting faster?
Right, and that
it wants to get away from us.
That's where Edwin Hubble came in. He basically said, yeah, this is really weird, guys, because some of these stars appear to have a velocity that's proportional to its distance from the Earth. Like, there seems to be some sort of rhyme or reason here to it.
Yeah.
And it suggested to Hubble, and later on to everybody else, including Einstein, as we'll see, that the universe itself was expanding. And this is where we came to the genuine origin of the Big Bang Theory. The idea that the universe was expanding, and
at a constant rate too, right?
Yes.
Is that the idea? Is that the Hubble constant?
No. The Hubble constant is the proportion between, or the relationship between how fast something is moving away from us,
right,
to its distance from us.
Well, yeah, I guess it didn't mean constant rate. I mean,
and actually, no, the universe appears to be expanding more quickly than it was before.
Yeah.
So it's increasing,
that's what I meant. But
makes a lot of people really
in its
nervous.
Relationship.
Yeah,
that makes sense.
Yeah, the Hubble constant has to do not necessarily with the inflation of the universe itself or the expansion of the universe itself, but how far or how fast, say, a star is moving away from us. And the further away from us it is, it appears to be moving faster than others that are closer.
Yeah, and we should point out, you said inflation and or expansion, and apparently if you're an insider, if you're a scientist, you probably say inflation.
Sure. So expansion is the basis of the Big Bang Theory.
Yes.
It's the idea that the universe has expanded over time, so that by logic, since time is one of the 4 dimensions that we live in, right? You've got the 3 dimensions plus time, so therefore space-time describes the fabric of the universe and the reality we live in, right?
That's right.
So by logic of that, if you went backward in time, the universe would be smaller and smaller and smaller, and the more they started looking into it, the more their minds started popping as they realized, like, wow, this thing was really, really small once. And that's the basis of it. Inflation theory comes in and suggests how that happened, how that expansion happened.
Right.
And it fills in a lot of blanks that we'll also talk about.
So you mentioned Einstein earlier. He's a noted smart guy.
Yeah.
And he actually had some issues, because it conflicted somewhat with his general relativity theories, because he subscribed to his own theory that the universe was static. It's not expanding.
Right. I think like he was like a member of there's a way of viewing the universe that like it was always this way, it was always spread out this way.
Right.
It wasn't getting bigger. That's nuts. And so he figured that his general theory of relativity would prove this. And actually, he was extremely surprised to find that his own general theory of relativity actually said, no, the universe is either expanding or contracting. It's certainly not steady. And then Edwin Hubble came along, and he had his findings, and Einstein said, you know what? I was wrong.
Yeah, I'm a big enough man to admit it.
Yeah, that's the kind of guy I am.
And one day, people are going to keep my brain in a jar in a barn.
And slice it up. It's going to go on a car trip. That was a good episode we did, too.
Yeah, did we do one on that?
Oh, yeah.
On its own?
Einstein's brain.
Oh, yeah, that's right. I remember. Boy, those were the good old days.
Einstein's brain episodes?
Sure.
Yeah.
All right, so let's talk about some of the predictions that rose from the theory that the universe is expanding. One is, and Strickland says, the universe is homogeneous and isotropic, which is a fancy way of saying it's made up of the same materials and completely uniform.
Yeah. Here is one of the first times we run into something where you're like, what are you talking about? It's funny, if you read Strickland's article, and I sent him an email saying as much, that I was like, this is really well written.
Yeah.
But if you just read the words you're saying, it sounds like it was written by someone who is totally insane.
Yeah.
You know?
I know.
And he makes the point, too. He's like, well, yeah, all you have to do is look out into the Milky Way or anything like that. Anything we can see easily and see that it looks different. Like, there's not a star that looks just like our sun with the same number of planets looking around.
Right.
The point is that you look, if you go out of several orders of magnification and look at the universe outside of any given galaxy, you're going to see that actually, everything's distributed pretty evenly throughout the universe. And so that makes it homogeneous. And then secondly, it's isotropic, meaning that there is no center to the universe. There's no central point.
Yeah, which some people posit that the Earth is the center of the universe. Well, we'll talk a little bit about that later.
Okay.
But that's wrong, right?
I mean, it hasn't been disproven, but it's just extremely unlikely, I think.
Yeah, I think it's a very human-centric thing to say.
But the reason why some people say that is that they are, if you look around, that expansion that we're seeing is everything's going away from us.
Right.
Which is like, why is that happening? Like, we should be going along at least with something else. But the idea is that we're not, because we're the center of the universe, but the implications of that are so mind-boggling that it's just not possible almost.
Yeah.
That we're actually at the center of the universe when we're just this small segment of a tiny bubble in a frothy sea that defies proportions. There's no way that's the center of the universe.
So another prediction was, we talked a little bit about the intense heat at the very first moments of the Big Bang. And if that were true, then you would feel and see this radiation, I guess not see it, but you would have this radiation expanded over the entire galaxy in roughly equal proportions.
Yeah, because again, remember, the universe is homogeneous and isotropic, so if there was radiation, it should be evenly distributed.
Yeah, there'd be like, they call it an echo, I've seen described in some circles.
Sense. Right, okay, so apparently back in the 40s, they detected this stuff and didn't know what they were looking at. And in the 60s, they figured out, holy cow, this is the cosmic microwave background, which is basically, I think of it as more like a fingerprint, the fingerprints of the universe, right?
Yeah.
And it's evenly distributed. It's this trace radiation that's still around from the Big Bang.
Yeah.
Which is pretty amazing. So when you put that and the discovery that the universe does seem to be homogeneous and isotropic, along with the fact that we discovered this cosmic radiation background that's evenly distributed throughout the universe, it really gives a lot of credence to the Big Bang theory. And so too does this gravitational wave.
Yeah.
The gravitational wave discovery, they apparently found curls in the cosmic microwave background that are remnants of gravitational wave from the Big Bang too. So it's just getting supported all over the place, and everybody's super happy about it.
Yeah, there's like real observational data there.
Right.
All right, we teased those first nanoseconds, nano moments after the Big Bang. So let's talk about them right now. The earliest thing that scientists can even talk about, like with a straight face, like later on when they're having drinks at the bar, I bet they talk about before this.
Right.
But if they're like on a podium in front of an audience, they can go back as far as, I'll just say the equation, even though it will make no sense to anyone. T equals 1 times 10 to the negative 43 seconds.
May I?
Yes.
Okay. So T equals the time after the creation of the universe.
Yep.
And as far back as they've gone is 0.000000000000000000000000001 second after the creation of the universe. That's how far back they've been able to trace the Big Bang.
43. Nice work.
Isn't that amazing?
Yeah.
That fraction of 1 second is how far back they've been able to figure it out. And so much happened in that first second, Chuck, that just fractions of that fraction are, like I said before, like different epochs in the era of, or the age of the universe. Like entire epochs happen in trillionths of a trillionth of a second.
I know.
It's just so mind-boggling.
I know.
I love it, though. Like, I've really given myself over to this. I was fighting it at first. Like, well, that doesn't make sense. I don't want to. How does that make sense? And I did look plenty of stuff up.
Yeah.
But I also just kind of was like, I'm just taking this on faith. Despite what NDT says, like, you do kind of have to take this on faith, especially if you're not an astrophysicist. And I just kind of gave myself over to it, and I love it.
You know what happens when my mind gets bent like that too far? I just have some pie.
Oh, that's good stuff.
Yeah.
What
just
kind?
Stare at the wall and have some pie.
What do you recommend?
Doesn't matter. Pecan.
Okay, so something super sweet, not fruity.
What's a fruity pie? Like
cherry pie or apple pie.
I like a good apple crumble pie.
Oh yeah, I do too.
But not like the one with the crisscross pastry on top.
I don't really discriminate against pie.
Sure.
I tend more toward the fruity section of the pie spectrum. And I tend to think of pecan like right in the middle.
Yeah.
But then on the other end, you have like your creamy and chocolate mousse pies and stuff like that. I tend to be on the other side a little more.
Or a good lemon pie, lemon ice box.
Yeah, it's good stuff.
What I don't get is the cheddar on the apple pie.
I've never gotten that either.
I've never tried it, so maybe I should.
Those people are obviously crazy.
I like sweet and savory together, so maybe I should give it a whirl.
Oh, yeah?
Do we have to start talking about this again?
Dip a French fry in a Frosty and call it a day.
All right, so at that point that you described, that, don't say all the zeros again, but at that at that point, the universe was tiny, tiny, tiny and small and dense and hot, and the area of the universe spanned a region of about 3.9 by 10 to 34 inches. Everything.
And that area, right? 10 to the negative 33 centimeters. Again, the average diameter of an atom, or roughly something like that, is 10 to the negative 10.
Yeah.
This is that much smaller than an atom, and everything that's in the universe now was encapsulated in that tiny little thing, whatever it was.
That's right.
And again, like, surely astrophysicists and cosmologists, when they were coming up with these calculations, are like, this can't be right.
Yeah.
And I guess over time, they were like, it seems to be right.
Yeah.
Either we're all just totally off our rockers and really somebody forgot to carry a one and everybody forgot to carry a one, or this is really how things started. And it's just mind-boggling to think.
All right, so in that very first moment, theorists think that those four primary forces that we mentioned are still hanging together.
Sure.
They're still united. And that matter and energy were inseparable at this point.
Which is another, don't feel bad if like you're sitting there going like, how is that possible? No one knows.
Yeah.
They just see, like, the calculations bear that out, is another way to put it,
That's right.
But that's how it was. Matter and energy were one and the same.
And as things expanded, and we'll go into these in detail, we go through something called baryogenesis, particle cosmology, and then standard cosmology.
Right.
And as this time passes, things become a little more easy to understand. And when I say easy to understand, I mean extremely difficult. But at least your mind can wrap around it.
Yeah. Start to, at least, right?
Yeah.
So remember, we started at T, which is the time after the creation of the universe. T equals 1 times 10 to the negative 43 seconds.
Yeah.
The next big part where things start, and actually, in between the two, gravity separated from the four fundamental forces.
Yeah, just a little thing like that.
Right.
Mm-hmm.
But the next big one that came along was at 10 to the negative 36 seconds. And this is where baryogenesis happened. And around this time also, this is where the electroweak, which is electromagnetic, and weak force combined together,
right,
separated from the strong magnetic force. And apparently here, at that 10 to the negative 36 power seconds, that was where inflation happened. That's where the expansion began.
Right, and that's where we actually could begin to observe some kind of matter.
Yeah, and they think that what happened was a tremendous amount of matter and antimatter were created.
Yeah.
But that, and we did it, I don't remember a lot about the details, but remember we did a podcast on antimatter spacecraft.
Oh, yeah.
How amazing those were.
Sure.
But antimatter and matter like to just destroy each other and effectively cancel one another out.
Uh-huh.
But apparently, at the beginning of the universe, at the origin of the universe, it's suggested by this that there is a slight imbalance in whatever makes matter and whatever makes antimatter, so that there was slightly more matter that was created than antimatter.
Which is a good thing.
So that stuff survived.
Yeah.
Had the balance been the other direction, there'd be slightly more antimatter than matter now, and who knows what kind of loopy, bizarro universe that would have created.
Seriously.
You know?
Or if there would have been anything at all.
So all that matter that survived is the matter that we see in the universe now.
Yeah.
And that's a lot of matter. So imagine, since this is just a tiny fraction of the matter that was created and destroyed by the antimatter that was also created, how much matter and antimatter was created at 10 to the negative 36 seconds.
Yeah.
Through baryogenesis.
Again, it's just mind-boggling.
And that was the result, Chuck, of energy and matter uncoupling as well, right?
That's right.
Okay.
All right, and this is the point where we can actually start to, we did one on the Large Hadron Collider. Mm-hmm. It's a particle accelerator, the biggest and best that we have on the Earth. And this is where you can actually use a particle accelerator to recreate and look at this stuff.
Right.
So we can actually observe this at this point.
Yeah, we can smash things together and be like, kaboom! Look at that! Early universe. That's what they do at CERN.
Oh, yeah?
Uh-huh.
All right. Well, people should listen to that one, too, by the way.
Oh, yeah.
That would be a good, primer.
That was the one where we wondered whether it was going to end the universe or not.
Right. It did not.
Not yet.
So at this point, there is still no light. Things are too dense, and it is still just a dark, dense area.
Right, exactly. And I think during the particle cosmology epoch, the electromagnetic force and the weak force break off into separate forces.
That's right. And we still can't, at this point, these subatomic particles still can't bond. They're there. They can form.
Right.
But they can't hook up and party.
Right, exactly. That actually didn't start to take place until we reached the standard cosmology age, which is the age that I believe we're in now, right?
Yeah, which started 0.01 seconds after the initial bang.
Right, 1/100th of a second. So we've gone through that many ages, and we haven't even mentioned them all.
No.
In within that first second.
Yeah, it's crazy.
It is crazy. So, that standard cosmology, this is about where the astrophysicists and cosmologists say, we understand it from about here on out. Right. Everything else is a little shaky, but we've got some observational data that backs it up. But here is where, neutrons and protons were formed, and, a little after that, they started to be able to form nuclei through nucleosynthesis, right? And they would ultimately be the building blocks of atoms.
Right. And so at this point, things are still expanding and cooling at a rapid rate, and we can actually, there are no atoms yet, but like you said, it's too hot at this point for electrons to complete that process.
Right.
Still too hot in the hot tub.
Yeah. I mean, after 100 seconds, the universe had cooled to a temperature, after 100 seconds, to 1.8 billion degrees Fahrenheit, or 1 billion degrees Celsius. That was how hot it was still after 100 seconds.
Should we take another break here?
Let's.
All right, let's do that, and we'll come back and explain the rest of it in great, easy-to-understand detail.
Brought to you by the Spam brand.
Some foods or TV shows just instantly take you back to your childhood. Spam Classic is one of those foods.
It's so 90s, but also so iconic that the sight of it sizzling just makes your mouth water.
Back then, we had Spam Classic, but today, there are 12 irresistible varieties to choose from.
It's like picking your favorite Boy Meets World episode. Impossible. There's Korean barbecue flavored, jalapeno, and 25% less sodium, just to name a few.
Spam brand. Sizzle pork and
Learn more and get sizzling at spam.com.
Hey, it's us, the Jonas Brothers, and guess what? We have some big news.
What's the news, Nick?
Huge news. We created our own podcast called Hey Jonas.
We invented a podcast?
Well, we didn't invent it. We just contributed to it.
We're the first people to do podcasts.
Pretty wide range of podcasts
starting a
out there.
trend.
But this one's extra special.
So how do we actually come up with the name Hey Jonas, guys? I honestly don't remember.
I think it was on a call about what we should call it, and
we were thinking originally calling it one of the early names of our band before Jonas Brothers.
This is how you guys remember it going down?
Yes.
I have a very different memory of this. We were talking about a bit for the podcast where people could call in and say, Hey Jonas, and then I wrote down on my little notepad, Hey Jonas, and offered it up as a potential title for the podcast. But thanks for remembering that, guys.
Listen to Hey Jonas on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts. Just listen. We don't care where you hear it.
Learning stuff with Joshua and Charles. Stuff you
All right, buddy, when we left off, things were expanding and cooling.
And they still are, actually.
The end.
Yep.
Nope.
Good night, everyone.
And everyone here's Neil deGrasse Tyson.
To take us home. So, 56,000 years after the creation of the universe, or after the Big Bang, we were at a temperature of 15,740 degrees Fahrenheit.
Nice and cool.
Or 8,726 degrees Celsius, right? After another 324,000 years, so at 380,000 years after, it had cooled down to 4,000, just under 5,000 degrees Fahrenheit and just under 3,000 degrees Celsius. And finally here, atoms started to form because protons and electrons could combine. And the other thing that happened too was the density had expanded out enough. The volume had increased, is a better way to put it. And the temperature had cooled so that suddenly the universe was now transparent. We could see through it. Up to this point, 379,000 years, you still couldn't see through it. It was too dense and too hot. And at about 380,000 years, it hits that point, and you can see it like we do now.
Yeah, we finally have light. At that point, those cosmic microwave background radiation that we talked about earlier, it's locked in. I don't think we mentioned earlier where we're at now, temperature-wise, just to kind of put it in perspective. We currently are at roughly negative 454.8 degrees Fahrenheit, negative 270.4 degrees Celsius.
Yeah, that's the temperature of space right now, right?
Yeah.
Yeah. So it's definitely cooled. Apparently it's still cooling, like it's still not at absolute zero yet, which is the lowest temperature, or the lowest activity that atoms will move at ever.
Right.
So it's still cooling and still expanding.
All right, so here's when things really heat up, or I guess really cool down. Sorry, bad pun. Strickland points out, for the next 100 million years or so, this is when the universe is really cooling, it's expanding, and then you have matter clusters together.
Yeah,
eventually forms gas, and this is the quick view. We'll dive into it. Those gases form stars. Those stars cluster into galaxies. And those galaxies cluster together into solar systems.
Right.
That's the overview.
And so what they think happened was, because this really doesn't make any sense. As a matter of fact, one of the criticisms of Big Bang theory is that it violates the law of entropy, that organizations become more disordered and chaotic over time.
Right.
And the idea that planets and galaxies and things formed.
It seemed like it became more orderly.
That's the opposite. Right, exactly. Yeah. And so they've really kind of looked into how anything would have formed at all. And what they think happened was that back in, say, the 10 to the negative 43 second era, there were quantum fluctuations, little vacuum energy fluctuations within this universe, this tiny little universe. And that as the universe expanded very quickly, those fluctuations grew tremendously in size. And the vacuum energy in the cosmic microwave background, those little fluctuations that are on there, were just different enough from the other spots in the universe that they had slightly more density and thus exerted slightly more gravitational pull than other areas. And so more matter started to attract around them, and they started to form stars. And the stars started to form galaxies, and planets started to form around them. And all of a sudden, what had just started out as little vacuum energy became ultimately universal hotspots where you could find matter clustered together, which explains why so much of it is deep space is just void.
Yeah.
And why some of it has stuff. Apparently it all began with these little tiny quantum fluctuations way back trillionths of a second after the universe was created.
So like a really cool dude at a party the size of all humankind, and he's so cool that people start hanging out with him, and then his party grows a little bigger?
Sure.
Is that a good way to describe it?
I think that's better than anybody could ever hope to.
So it's an attraction basically that drew things together ever so slightly enough to form larger bodies and then larger bodies.
Yeah, and the reason why they think this happened is because these tiny little fluctuations, little details in this little universe, grow bigger over time, right? Especially if you look at this inflation growing as a process of time rather than just like volume expansion. It's also time is a dimension to it, right?
Yeah.
So it makes total sense in that just these little things would get bigger as the universe itself got bigger too.
Well, does that mean that the universe, and I'm being coy here, does that mean the universe will ever expand for all of time infinitely?
So, I mean, you're talking about like that debate, right?
Yeah.
Yeah, there's a whole debate over whether or not it's ever going to stop. And all of it comes down to how much matters in the universe, which we don't quite know yet.
That's right.
When they calculate the matter we do know about, they realize that there's actually some that you can't account for, and that's dark matter, because we know that there's something that's making stars behave differently, or there's clearly some matter that we can't detect that's out there.
Yeah.
So we can't account for all the matter in the universe, so we don't know how much matter's in the universe.
Right, but the idea is if there's enough, then that gravity will reverse and things will start to contract again, right?
Right, because gravity is this force that attracts matter to other matter.
Yeah.
And yeah, eventually, if there's enough matter, it'll counteract that expansive force that came out of it. And then, yeah, probably will either stop, is one school of thought.
Right.
Or the universe will contract and form what's called the Big Crunch.
Right.
And some people say that's what our universe is. It's just the cycle of expansion and contraction that takes place over many billions of years, but we're just one part of a cycle that is ongoing perhaps forever.
It makes it sound, when we talk about it like that, it makes it sound like the universe is just breathing.
It does, doesn't it?
Yeah.
Yeah.
In a creepy way.
Yeah. And Chuck, that has to do also, the reason why they don't know if it's going to keep expanding or contracting, they don't know if it's what's called a closed universe with positive curvature or one with negative curvature, right? And it also has to do with the shape of space to a certain degree. And Strickland also wrote a really top-notch article called Does Space Have a Shape?
Yeah, that's a good one.
It really is. And something from studying this that they figured out is that really it doesn't seem like it has a positive or a negative curvature. It seems flat. It seems like it has a zero curvature.
Right.
And this is what's called the flat problem of the Big Bang Theory. Why should it be flat? That doesn't make any sense, because if you look at the spectrum between positive curvature and negative curvature, there's a lot of places on that spectrum where the universe could fall one way or the other. But it's so close to the middle that astrophysicists and cosmologists have no idea if it's positive or negative in its curvature.
Right.
And they've started to wonder, like, why should we be almost exactly in the middle? That doesn't make any sense.
Right.
It would suggest that the early universe was so finely tuned that we're only slightly off of center.
Right.
So it would have had to have started almost completely at center. Because remember, small fluctuations grow bigger and bigger over time and on a larger scale. So since we're still so close to center right now, with the universe as big as it is, it would have had to have been basically on top of exactly in the middle between a closed and or a negative and a positive curvature at the very beginning of it, which is kind of puzzling in and of itself. That's like, well, that indicates some sort of weird fine tuning.
Yeah.
So does that mean that the astrophysicists are off a little bit in their own fine tuning of the Big Bang Theory and inflation, or what? Who knows? Or is there a little kid with a lighter who set the snake off?
That's right.
And the snake was very well manufactured.
Well, that's just one thing that we can't quite explain. We talked earlier about the fact that at the very beginning, that the Big Bang Theory wasn't meant to address a lot of questions. One of which is that we touched on was what happened before the Big Bang, and we just don't know.
It doesn't even try. It doesn't. It can't right now.
Yeah, that like trying to explain time before timing existed is futile.
Right, because you get into stuff that I just suggested, which is basically amounts to intelligent design or whatever, and that's beyond science. Like, science isn't equipped to say, oh, well, what about this or what about that? And I tried really hard to get Neil deGrasse Tyson to say something, and he was not going to bite.
Well, no, and smartly, I think a scientist looks at the observational data and extrapolates from there, and I'm sure, like I said, I'm sure, and I think he even said in the interview that, sure, people like to talk about these things.
Right.
But, it's not like, hard science.
Right. And also to answer that flat problem that I brought up, apparently inflation theory does answer it. It does satisfy it by saying the universe appears flat to us because we're looking at it strictly on a very local level, even though we're looking at 90 90 billion light years or something like that.
Right.
It's really just a very small segment of something. So if you take a balloon and you blow it up,
yeah,
it's still curved, but if you're just looking at just a pinpoint segment of it, it's going to appear flat to everybody looking at it from just that tiny perspective. So it's basically our perspective that we're looking at the universe right now makes it seem like it's flat, but it's really actually curved one way or the other.
Right.
That's the answer to that.
Well, should we talk about some of the problems with the Big Bang Theory?
Sure.
There are criticisms, and there will continue to be. One was that it violates the first law of thermodynamics, that you can't create or destroy matter or energy. And proponents will say that that's unwarranted for a couple of reasons. One is, like we already said, it doesn't address the creation of the universe. It was never meant to, but just how it evolved or inflated over the years, over the 60 or 70 years.
Right.
And another reason is, kind of like we said earlier, is that the further back you go, the rules don't apply. So maybe the law of thermodynamics is just completely moot.
Right.
When you go back that far.
Yeah.
Like it didn't come into being until later.
Yeah, if matter and energy are like one and the same, I can imagine that some of our current laws don't necessarily apply.
Yeah, well, probably a lot of them.
Right. And then one of the other things too is that that inflation that supposedly happened when the strong nuclear force decoupled from the electroweak force, and the universe suddenly expanded. You know, within that 1 second, it just kept growing and growing and growing.
Yeah.
Way faster than the speed of light.
Yeah.
And a lot of people are like, wrong. Nothing can go faster than the speed of light.
Well, there was no light.
Well, nothing you could see. Yeah, there are definitely photons, but they had the proponents of Big Bang have the same answer. They say, well, again, dude, you're talking general relativity. That wouldn't have applied at all.
Yeah, the answer is kind of consistently, don't even come at me with that.
Right.
Your laws.
Yeah.
Should we finish with a few other alternative explanations?
Yeah. Like we said, there are alternative models, right? One of them is that same one that Einstein was a proponent of, the steady state model, that it is not actually expanding. And apparently this is hard for me to wrap my mind around. The people who say that it's not expanding explain away expansion by saying that matter's created as in proportion to the original density of the universe.
Right.
So maybe the universe is expanding some, and more matter has to be created to keep the same density. So I think what they're saying is
that's what it means,
the universe has been at the same density all the time.
Right.
And sure, it's expanding, but it's also creating more matter.
Right.
So
which holds it static.
Yeah. Guess so.
The epyrotic. Epyrotic.
I know those two letters should not be. Epyrotic?
Epyrotic model?
Yeah, I think that's it.
Man, we're the worst. That suggests the universe is the result of a collision of, that's the one you brought up earlier, of two three-dimensional worlds, and that there is some hidden fourth dimension out there.
Well, that's part of, the fourth dimension is part of, like, standard astrophysics and cosmology. But this was like, this thing says our universe came out of two universes colliding.
Right.
In the fourth dimension. Which that defies me a little bit. But the idea that there are four dimensions and one of them is time is definitely a part of, like, standard stuff.
Right.
Still hard to think of.
Sure.
And then plasma cosmology, I like that one a lot because it's just totally different from the way we think of the universe. It seeks to describe it based on its basically its electrical charge state. You know?
Okay.
Rather than like the temperature of it or the density or anything like that. It's more involved in like the plasma aspects of it because, you know, plasma is ionized gas.
Yeah.
And it's like a fourth state of matter. And plasma cosmology looks at it through that lens, which is basically totally alien to everything we just talked about from what I can gather.
Did you just say there's totally aliens out there?
There's aliens out there, and the universe was started by a little kid with a lighter.
Wow.
That's my stand. Well, if you like this, then stick around because right now, Chuck, we have an interview with Neil deGrasse Tyson. We weren't joking.
Yeah, great job on that one too, buddy.
Thanks, man. We missed you. He was like, "Where's Chuck?"
No, he didn't.
Yes, he did.
Well, how you guys doing?
Good. How are you doing?
Are you assuming I know how stuff works?
I have an inkling that you may have a clue.
Okay.
So I guess my first question is then, how do you think of the universe when you think of the universe as a whole? Like, do you think of it as something like a speck of dust underneath a giant fingernail, or is it part of a branching multiverse, or is it a bubble that kind of pushes up against other bubbles? Like, what is the universe when you think of it?
I don't think I think of the universe in a fundamentally different way from that of my colleagues. What you want to do is separate the things we have data and observations to support, and the things that live and thrive on the frontier of theorizing about what the universe was, is, or will one day be, or what larger system it could be a part of. So if you live in the realm of data, then we are in an expanding universe, and it's been expanding for nearly 14 billion years. And it was smaller in the past and hot in the past, and it's getting larger and cooler by the minute. And we exist on this planet we call Earth, born 4.6 billion years ago, with the rest of the solar system, in some undistinguished part of an undistinguished galaxy we call the Milky Way. And this scenario, this picture, was very hard earned, and it's no more than about 80 or 90 years old in total. Mm-hmm. Edwin Hubble, the man in this particular usage of the word, Edwin Hubble in the 1920s, so about 90 years ago, 1926, discovered that there are other island universes, if you will. Not the way we might think of that term today, but back then, there were these spiral fuzzy things in the night sky, imagined to be just spiral fuzzy things in the Milky Way. He would show that those spiral fuzzy things are not in the Milky Way, they are entire other Milky Ways, other galaxies. And that was a profound expansion of our worldview, if you would. And then just 3 years after that, he would show that these spiral fuzzy things are rapidly moving away from us. Coupled with Einstein's general theory of relativity, we would learn that it's not just galaxies spreading apart within a pre-existing space. It is the fabric of the space and time itself that's expanding. All of this is supported by data. So if you have discomfort thinking that the universe had a beginning and that we will expand forever, then too bad. That's just what the universe says. And the universe, I've said this before, the universe is under no obligation to make sense to you, especially when what we learn of the universe comes to us from methods and tools that completely transcend our native inborn biological senses, which in fact is the great ascent of science.
Sure.
What are all the ways we can decode the operations of nature without having to rely on the limits that our biological senses force us to occupy?
So when science is furthered, decades down the road, and the vision we have or the view we have of the universe we live in is magnified by orders of magnitude from what we're looking at it through right now. What do you suspect what shape do you suspect it's going to take? Do you have suspicions? And if you don't, how do you keep yourself from making that leap? Like, yes, of course, this is what it's going to be. This is what we're really living in.
Well, we all have biases, and let me not call them biases. Let's say we all have longings for how we think or want the universe to be. And if you begin to believe your longings too strongly, then you might miss some realities that don't fit your expectations, and someone else will catch them and make the discovery. So it's okay to lean in one direction or another, but don't do so while being blind to what else could be true, in spite of how you think it might be. Sure. So now the scenario I gave you is very well established in terms of observations and data and basically a century of thinking about and observing the universe and posing questions and answering them. So beyond that, we can ask, is there a multiverse? All right, this seems to come naturally out of certain thinking about the behavior of the universe when you try to bring together quantum physics and Einstein's general relativity. There are good arguments to suggest that we could be in a multiverse, and it's not obvious, at least to me, how one would test that just yet. And so, but the theories of the universe that point to a multiverse are themselves well tested. So this is what gives you the confidence that maybe our multiverse folks are onto something. And there are other frontiers. For example, the quantum physics, which is the theory of the small, and general relativity, the theory of the large, they work perfectly well in their own regimes. General relativity describing the large-scale universe, quantum physics describing, with very high precision, atoms, molecules, nuclei, particles, this sort of thing. But in the early universe, when the entire universe was the size of an atom, then we might suppose that quantum forces override whatever was going on with general relativity, because now the entire universe is of the size that quantum laws significantly manifest. And right now we do not have a good way to merge those two theories. And we got top people working on it. So these are collectively the string theorists and others in that realm who are thinking long and hard about, is there a third theory that needs to be introduced that will enclose quantum physics and general relativity into a deeper, broader understanding of what's going on, or will quantum physics absorb general relativity? I don't know that people know just yet, and it involves very high levels of math and higher dimensions and this sort of thing. And some people have criticized string theory for not really being a legitimate theory because you can't test it in any traditional way. But it's the only game in town, and they're not very expensive. You give them a pencil and a pad and throw in a laptop, and a string theorist is in business. So I let them go as far as they can take it.
So it does seem like there is either, like you said, quantum physics may be the answer to all this. We just don't fully understand that field yet enough to get back to the moment of the Big Bang or what happened before the Big Bang. But it could also be, from what I've seen, the unified field theory that gets us back to that point. But either way, to get to a point where we go further beyond our current understanding, further back in time in the Big Bang, including before the Big Bang of what was before, it seems like it's going to take a vast leap forward. Do you think that leap is going to come from a genius that hasn't been born yet, or has been born but hasn't been educated and entered the field yet? Is that how it's going to happen? Or is it going to happen from, this person combining this work with this work and that work and this work, and then suddenly the pieces are going to fall together in that sense?
That's a great question that also has a philosophical dimension to it.
Sure.
Such that in modern times, great leaps in science, do they happen by the lone genius burning the candle at midnight, coming up with a eureka moment, or do they come about because you have huge, expensive, highly collaborative scientific projects, such as LIGO discovering gravitational waves,
right,
such as the next generation space telescope. It's called the James Webb Space Telescope, not yet launched, but that will enable us to see galaxies being born in the early universe, as well as a host of other frontier observations that were not possible with previous telescopes. Well, that telescope had to be designed by whole teams of people with questions that they had in mind that they want answered by the new data. So I'm not convinced that we're just waiting for a new smart person to come along and have it all make sense. Mm-hmm. I think we're waiting for someone to obtain new data that we've never seen before that then force us into new ideas and understandings of the universe. Maybe there's some new theory that maybe I'm not discounting it, but what I can tell you is we're in an era. Look at the Higgs boson, for example. That required the Large Hadron Collider and thousands of scientists and tens of thousands of engineers who built the thing in the first place. So we're kind of in a collaborative era right now, and so if I were a betting man, I would say that the great discoveries to come will come about from huge collaborations, possibly even international collaborations. Now, that doesn't remove the question as to whether there is an Einstein walking among us who happened to have been born into poverty in a developing country, and then we will never know. Well, that would be one of the great tragedies of modern civilization. So I, as an educator, feel very strongly about what kind of access people of the world should have to knowledge, to learning, to health, to a person should be able to live a day and not have the entire day be preoccupied about whether you have food or whether or not you're going to die from a disease that your neighbor just died of. So this is so I think we should be able to measure our state of our civilization by the extent to which we are in the position to discover another Einstein rising up from the midst, and that's one way to get an Einstein. Another one is to wait around until one is born into the right circumstances.
Right.
But I'd rather we've got 7 billion people on Earth. Somebody in there's got to be badass enough to help us out.
So you brought up your role as an educator, and you're a world-class science popularizer and explainer. What is it that got you into science as a kid?
I was 9 years old, and it was a first visit to the Hayden Planetarium right here in New York.
Oh, that's
but
fantastic.
My local planetarium. I think most big cities have planetariums. Even medium-sized cities will have a planetarium. And my family, my parents took my brother, my sister, and me to all the cultural institutions of the city every weekend. So one weekend it was the Natural History Museum, another it was the zoo, another it was the aquarium. We even went to other things that sort of talented grown-ups did, like we'd go to a baseball game or the opera or the theater. And that exposure enabled the three of us to see what is possible beyond the traditional, you want to be a doctor, lawyer, Indian chief. The three traditional options that you're given as a 6-year-old or a 7-year-old. And so out of that arose my interest in the universe that really got cemented by the time I was 11. I knew that, in fact, I was so convinced that I wanted to do astrophysics that I began to question whether or not it was in fact the universe that chose me.
That's really cool. Well, thank you very much, Dr. Tyson. We appreciate you joining us. This was like you just took our Big Bang episode and moved along light years. So thank you.
Oh, okay.
Thank you. And
light year's not actually very far in the scale of the universe. So I'd feel better if I'd taken it along billions.
How about a parsec or something?
A parsec is only 3.26 light years, so that still won't even.
All right. Billions
we live
of
in
light years.
And a parsec is not even far enough away to get to the nearest star to the sun.
Okay.
So you're just in the wrong zone there.
Okay, well then, how about billions of parsecs?
Nice.
Okay. Thank you very much. What a guy, huh?
Great job.
Yeah.
He's just such a cool customer. That's why he is where he is now.
Yeah, and if you want to hang out with him, head on over to the Hayden Planetarium. I'm sure he'd be happy to see you.
Sure.
You can see him on tour. You can see him with Star Talk Live. He's got a podcast, for those of you who don't know, with our pal Eugene Merman.
He was on our TV show even.
He was. I didn't get
Briefly.
a chance to ask him if he remembered that
I'm sure
or not.
he didn't.
That's why I didn't get a chance.
Yeah. That just would have been embarrassing.
Well, if you want to know more about the Big Bang, type those words into the search bar at howstuffworks.com, and they'll bring up some great stuff. And since I said search bar, it's time for listener mail.
I'm going to call this, Is Russia European?
Nice.
Remember that debate?
Sure.
Well, it wasn't so much a debate. We just kind of wondered.
Right.
In the Continents episode, hey guys, thanks for cracking me up with the show. It's astonishing how many film references you can fit into a geography lesson. Yes, Russia is definitely a European country! ! Historically, it's always been considered a part of Europe. For example, it was named as one of the 6 major European countries in World War I, and the Tsar was closely related to other royalty in Europe. This is very different from China or India, always much more distant and mysterious to the east. Also consider that maps are very deceptive. Over 75% of Russia's population is on the European side, including every major city from Moscow to St. Petersburg.
From Milan to Minsk.
I knew you were going to say that. Very nice. I would have been so disappointed had you not. Most of the land you see to the east is empty and largely uninhabitable, only there to look pretty on a map. Well, I don't know about that, but
that's what the little kid with the lighter put it there for.
So cheers. That is from Timothy, and that was one heck of a Seinfeld reference.
Timothy or Timothy? Is he Russian?
No, good point.
Yeah, it's Timothy Moscow, who just wrote it using his pseudonym Timothy.
Milan to Minsk.
If you want to get in touch with me and Chuck and Jerry, you can tweet to us at SYSK Podcast. You can join us on Facebook.com/Stuff You Should Know. And you can send us an email to stuffpodcast@howstuffworks.com. And as always, join us at our home on the web, stuffyoushouldknow.com.
For more on this and thousands of other topics, visit howstuffworks.com.
Brought to you by the Spam brand.
Some foods or TV shows just instantly take you back to your childhood. Spam Classic is one of those foods.
It's so 90s, but also so iconic that the sight of it sizzling just makes your mouth water.
Back then, we had Spam Classic, but today, there are 12 irresistible varieties to choose from.
It's like picking your favorite Boy Meets World episode. Impossible. There's Korean barbecue flavored, jalapeno, and 25% less sodium, just to name a few.
Spam brand. Sizzle pork and
Learn more and get sizzling at Spam.com.
#1 hits, millions of records sold, awards, sold-out tours. You think the Jonas Brothers are satisfied? Nope. It's podcast time.
We get to ask other people questions because we're sick and tired of being asked questions.
Hey Jonas is available now, and their first guest is a big one, Paul Rudd.
You know, Steve Carell is a great singer.
Can he tell you not to audition for The Office or something?
I told him.
Whoa.
We were filming Anchorman. Clearly, I was the idiot. Thank God he didn't listen to me, right?
Listen to Hey Jonas on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts.
This is an iHeart podcast. Guaranteed human.